Hi, I'm Charles. So last year I found a bug in the Glibc while working on PHP, which is a thing that I do a lot. And I used the bug to attack PHP through a binary bug remotely in 2 different ways, and this is what I'm going to show you today. Hopefully we'll have time for the 2 ways, but normally I don't think we will, sadly. So, a quick summary of what we're going to talk about. First, I will tell you how I found the bug. It's really not only an introduction, it's also a way to tell you about what you can do when you have a favorite primitive in PHP. Then I will tell you how you can attack PHP filters with the bug that I found. If you don't know what this is, I will tell you what this is, don't worry. And then hopefully we'll have a few minutes to talk about another way of attacking the bug using direct calls to Iconv in PHP as well. And then again, hopefully some time for the conclusion. So regarding the discovery, well, we first need to understand what you can do when you have a favorite primitive in PHP. So, for instance, you are doing some kind of code audit and you find this piece of code. So obviously there's a bug, there's a favorite primitive. You can read, force the server to give you a file. So what you can do with it is obviously read a file, right? You can read etc password. That works. It's cool. It's already a very good bug. But since it's PHP, you can also do like network requests. So you can ask it to read an HTTP resource. That will work as well. And you can also ask it to read an FTP resource. That will work. So you have a favorite primitive, but it's actually also an SSRF, which is even better. But since it's PHP, it's even better than this. You have a few custom protocols, such as //. And what // does is that it will let you access the contents of a file archive. A file archive, it's a PHP archive. It's the same as jar for Java. It contains source files, resources, but also serialized metadata. And when you access a file file using // you will have the metadata that gets deserialized. And arbitrary deserialization, as you may know, is not very good. Generally, it gives you RCE. So a go-to attack for the longest time for PHP was that if you had a favorite primitive, you would find a way to upload the file to the server so that you could upload a file file with arbitrary serialized data into it. And then you would use the file read to access the file file using // and you would get arbitrary deserialization and you would probably be able to get remote code execution this way. But now it's very much harder to do because starting from PHP 8, which came out, I think it was 4 years ago, there's no more deserialization of the metadata when you access a file file using // The reason is that they don't actually use the metadata, so it makes absolutely no sense. And also, big frameworks such as Magento are disabling the // protocol because they don't use it and they know how dangerous it is. And in addition to this, but that's probably a subject for another talk, so I won't talk about this too much, but I think deserialization is going to get really, really harder in PHP in the next few years. I think in 5 years it's going to be really, really hard because types are making a comeback and types are really hard to bypass when you're trying to attack deserialization. And also the gadget chains are being patched more and more, which is pretty annoying. So, far is basically gone, so we needed to find a new way to attack file reads in PHP, and a way to do that was to use another PHP protocol, which is PHP // filter. What it does is that it will let you read a resource, but apply transforms onto it before it returns it to you. To give you a better idea, let's have a look at this filter. So it's PHP // filter / convert.base64 encode /resource equals etc password. What it does is that it will read the resource, etc password, and then apply the filter onto it. The filter is convert.base64 encode. What it does is that it will base64 encode the file. So if you read such a file using a PHP function, it will read the file, convert it to base64, and return it to you. So it was meant for developers, but I've never seen any developer use this. It's actually a tool for hackers mainly, and you can stack as many filters as you want. You can have 1, 2, maybe 1,000, like there's no limit at all, which makes for a lot of interesting bugs. But we're talk about this a little bit later. So obviously you cannot only base64 encode, you can base64 decode, but you can also put the string in uppercase using string.upper, put it in lowercase. You can do some very old crypto with string.road13. That's the CZ encryption. I don't know why it's there. Also there's dchunk. We're going to talk a little bit about that later. And also there's the one that's really interesting to us today. It's convert.iconv.x.y. What it does is that it will convert from one charset X to the charset Y. And the name Iconv is due to the fact that to do so, it uses the Iconv library, which is part of the Glibc, which is the main library for Linux programs. So, just to give you an example about this filter, say that you're reading a TC password and you want to convert it to UTF-16 for some reason, and you assume that it's UTF-8, which is it's probably the case. So what you do is you read php://filter/convert.iconv.utf8.utf16/resource equals UTC password. And what it will do is read UTC password, convert it from UTF-8 to UTF-16 and return it to you. So that works fine. And people have actually been using all these filters to do really like funny things with PHP files. And myself, what I wanted to do was try and see if we could add from a given file an arbitrary prefix and suffix to the files so that we could make it look like something else. The idea is that if you have a file read primitive such as this one, where the file is then going to be passed as something, for instance here it's passed as JSON, if you read etc password, obviously it won't work. But if you can transform the file using filters so that it looks like JSON, well, you're going to be able to read any file because PHP is going to think that any file is actually JSON. And I actually managed to do so. The name of the tool is wrap. It's written at the bottom if you're interested in it. But the important part in all of this is that when I was researching for the tool, I had not much of an idea of how filters and character set conversions worked. So I started building a few brute force scripts. So I built a brute force script that started from a charset A and then converted to B, then to C, then to D, etc. Just to have an idea of what character set conversions would do to a file so that I could find like interesting things. And after a while, so I was like brute forcing using PHP and I got a crash. Like not a PHP fatal error, but a real crash, like the program crashed. And that was really strange. But at the same time, it was PHP, so I was thinking that it was due to PHP, right? And it wasn't actually, it was due to the glibc. As I've said before, Iconv, this is the library that PHP uses to do the conversion. It's part of the glibc. And what it does is that it takes an input charset and an output charset, and then you give it an input buffer with some size and an output buffer with some size. And what it does is that it converts from the input charset the input buffer into the output buffer. And it always guarantees that it will not read too many bytes from the input buffer or not write too many bytes into the output buffer. Otherwise you have a buffer overflow. But sadly, in one single case, they actually mess up and you actually get a buffer overflow. And to get the buffer overflow, you have to convert to a very specific charset, which is ISO 2022 CNX, which I didn't know about before. It's an extended Chinese character set. And in some cases, it will try to write escape sequences to switch in between panes of the charsets. We don't really care about this. But when it does so, it actually needs to check that there is enough space in the output buffer to write the escape sequence, right? Because otherwise it will write out of bounds. And it does so nicely in some cases, but in other cases it doesn't. And so that means that as an attacker, you may get an overflow of 1 to 3 bytes using Iconv, but these bytes are not really controlled. These bytes, they can be either $*H or $+I or $+J or $+K, etc., etc. That's all the 6 values that these bytes can have. Okay, so the bug is really bad because we need to convert to an arbitrary charset. We get an overflow that we don't control the bytes in, and we don't actually control the size of the overflow either. So it's really bad. But still, it's an overflow, so we try to exploit it, right? And a good way to get this bug is to use Chinese characters. So as you can see here, I know they are Chinese. I don't know what they mean. They give you an overflow. That's all I know. And so yeah, again, the vulnerability, it's a 1 to 3 bytes overflow, so 1, 2, or 3 bytes. Fixed byte values. So really bad. And in addition to this, you need to control the output charset. You have to set it to ISO 2022 CNext. So it's hard because nobody uses it, honestly. Again, you have to control part of the input buffer to put in the beautiful Chinese characters. And also you have to have a suitable output buffer. And what I mean by that is that if the output buffer is way bigger than the input buffer, you will not be able to reach the end of it, so you will not get your overflow. And all these conditions make for that bug to be really hard to exploit. I would happily show you like a few targets that I had, such as Glibc Summer 2, but it actually didn't work in the end. But we don't really have time, so I will go straight up to attacking PHP filters, because that's the only thing I could crash, actually. I got a crash without even trying. And so I focused on this and tried to convert a file read primitive in PHP to RCE using this buffer overflow. So to understand what I'm going to talk about, we need to understand the heap of PHP, which is a custom heap. It's very simple to understand, so don't worry. So it's page-based. There are 512 pages, and they all have a size of 4096 bytes, so 1000 in hexadecimal. And each page contains chunks of the same size. So for instance, in some executions, page 10 will have chunks of size OX100, page 11 may have chunks of size OX30, anything, you know, but it's a chunk size for each page. And then for each chunk size, there's a free list that is stored as a singly linked list, and it's last in, first out. So when I free a chunk, PHP will check its size and put it in the appropriate free list. It's very similar to the TKH of the libc, but without any protection and completely unlimited. So to visualize this better, let's have a look at this image. So on the left, you have the heap, 512 pages. The first page is metadata, so we don't really care about it. But then in every other page, you can have some specific chunk size. In my example here, page 5, there's the chunk size OX400. So that means that you can store 4 chunks in page 5. And we can see in the middle that we have chunk 1 and chunk 3 that are allocated, but chunk 2 and 4 that are not. Which means that chunk 2 and 4 are part of the free list for chunks of size OX400. Since they are part of the free list for this chunk size, that means that they all have a pointer to the next free chunk in the first 8 bytes, as you can see on the image on the right. So if I have an overflow that starts from chunk 1 into and goes into chunk 2, that means that I'm going to be able to overwrite at least 1 byte in the address stored in chunk 2. And this is a very good point for starting an attack, because we are altering a free list, and altering a free list generally means that at some point you're going to be able to have an arbitrary write, and arbitrary write is really close to code execution. So the PHP heap, it looks pretty easy to exploit. Like, there's no protections, it's page-based, like it's really easy to understand. But the problem comes from the fact that there's a one heap for one request policy in PHP. So when you send an HTTP request to a PHP server, it will create a new heap, allocate your HTTP parameters into it, then run the scripts. So that means compiling the script, compiling thousands of files, well, hundreds of files, and then running the script. So thousands of allocations, the allocations like completely messing up the heap, and then it will return the HTTP response and then delete the heap entirely. So the problem is that the bugs, they will not linger. If I manage to corrupt the heap using one PHP request, I have to also use the memory corruption in the same request, because otherwise the bug will be gone on the next one. And this is what makes it really hard to exploit PHP. And to give you a better idea of this, you also have to understand that in between the triggering of the bug and the usage of the bug, you cannot inject any more data, you know, because you've sent your HTTP parameters and that's it, like the script is running by itself. So you need to find a way to send HTTP parameters that will trigger the bug, also set up the heap beforehand, and then also use the bug at the same time during the execution of the same script. This is what makes it really hard to exploit binary bugs in PHP remotely. But now we have a better idea of how the heap works, so we can actually have a look at PHP filter. So it works really simply as well. What it will do is first read the resource as a stream and then apply the filters onto it one by one. So to read the resource as a stream, it will parse it in a structure which is called a bucket brigade. A bucket brigade is a collection of buckets. each bucket can store a buffer of some size. So, for instance, if I ask it to read etc password, it may allocate a first bucket that contains the 5 first bytes of etc password, then another bucket that stores, I don't know, like 10 more bytes, and then a third bucket that stores like the rest of the bytes of etc password. So that's a way of representing a stream, a collection of buckets. Once it has done this, it can start applying filters. So it takes the first filter, it takes the first bucket, and it applies the first filter on the first bucket. And then it applies the first filter on the second bucket, and then on the third one, and it gets a new bucket brigade. And now it can apply the second filter, and then the third filter, and the fourth filter, etc., up until it's done. So it doesn't look too hard to exploit now, right? Because we have the ability to read binaries. After all, the main point for the exploitation is a file get contents, a call to a file read primitive. So we can use it to read binaries. We can read the Glibc. We can even check if it's patched. Like we download it and we check if it's patched. So it's really nice. Also, we can beat ASLR and Pi really easily because we can read proc self maps. So we don't really care about like memory randomization. And also that gives us a good thing as well, which is that we know the address of the PHP if section. We're going to be using this afterwards. And the last good point for us is that it kind of feels like we can do arbitrary allocations and deallocations because there's the bucket brigade technology and we can add as many filters as we want. So we kind of feel like that using filters, we can resize buckets or create new buckets or remove buckets, etc., etc. But it kind of is a web exploit, so I want a web exploit. I don't want something that crashes. I don't want something that I have to rebuild every time I'm targeting a new environment. I don't want to change the exploit if it's targeting PHP 7.0 or PHP 8.3. I want something that actually feels like a web exploit. You know, you start it, it says yes or no, and you get your shell. No crashes. So how do we do this? Well, the first problem that we face, and this is really annoying, is that I told you about having a bucket brigade technology in PHP, so you can have like 10 buckets, but actually when PHP reads a file or anything really, it will only allocate one bucket. So it can have several buckets, but it will only allocate one. So if you read etc password, you get one bucket with the whole file. If you read an HTTP resource, you get one bucket with the whole HTTP response. Same for FTP, same for file, same for anything. You only get one bucket. So it's really, really hard to exploit with one bucket because you cannot spray the heap. You basically have two allocations, the bucket and the one that gets created to filter into. So it's really, really hard to exploit. Not impossible, but really, really hard. And so we kind of need to find a way to have several buckets instead of only one. And a good way to do this is to use the zlib inflate filter, which will decompress the stream. And what it does is that it takes your stream and then allocates an output bucket of 8 pages. If the output bucket of 8 pages is too small, it creates a new bucket to store the rest of the decompression. If it's too small, it creates another bucket, etc., etc., etc. So what you get from this is a single bucket that gets converted into many buckets, which is nice, but the buckets, they all have the same size, which is 8 pages, and 8 pages is very inconvenient for exploitation. So we need to find a way to resize these buckets afterwards. To resize these buckets, we can use another filter, which is called dchunk. I was telling you a little bit about it beforehand. It is undocumented, but it's very much used by attackers, so it's pretty well known. And what it does is that it will decode a string that is HTTP chunked encoded. What is HTTP chunked encoding? It's very simple. The idea is that you send the size, then the new line, and then the data corresponding to the size. Then you send the new size, then the data, then a new size, then the data. Okay? So if we pass the example here, it sends 8, which means that it's going to send 8 bytes. Then it sends 8 bytes. Then it sends 11, which is 17 in decimal. So it sends 17 bytes, and then D, which is 13, I think. And so it passes 13 bytes. So the result of this is how the chunked encoding works. And at the end of this, you have 0, which indicates not an empty chunk, but the end of the parsing. If it sees zeros as a size, it stops parsing. So it's good for us, right? Because now we can resize our buckets. If we want bucket 1 to have size of 148, complete random example, we write 148, a new line, then 148 bytes. then a new line, and then 0, a new line to indicate the end. If we want the second bucket to have a size of 100, we write 100, new line, data, new line, 0, new line. And we do this with every bucket. And then we call dchunk, and we kind of expect it to work, but it doesn't. And the reason is that in bucket 1, we tell it that the stream is done because we've written 0 and as a size. So it will not process bucket 2, it will not process bucket 3, etc., etc. So we go back to the initial problem where we have one bucket with an arbitrary size, which is completely useless. But luckily for us, we can actually pad the size with thousands of zeros, so that in each bucket, instead of having a size, some data, and then 0, we only have a size and some data. Okay? So we pad our original size, which is 148, with like thousands of zeros, so that it does almost 8 pages of size. Then we add the data. And in each bucket now, we only have one size and one data. So it's going to be able to parse each bucket sequentially, and it will work. So now we have a way to create as many buckets as we want and resize them to the size that we want them to have, which gives us a very good starting point for exploitation. But we're not done yet. Now we are actually facing the hardest part, which is building a real exploit algorithm without being able to interact with the server. And to do this, we kind of want to be able to allocate and deallocate chunks at will, which we are not yet able to do. We can create many buckets, but we don't control their size immediately. So a good way to do this is to actually focus on one chunk size. If you focus on chunk size 100, that means that since the allocation is page-based, every chunk size, chunks that has a bigger size or a smaller size, it doesn't really matter. Like you're not going to be able, like you're not going to be seeing it in your exploitation process. So if you have this abstraction in your mind, that means that when you have a chunk that gets resized to the size 100, that means that it appears, basically. If it gets resized to a smaller size afterwards, it means that it disappears. So it's basically the same as being able to allocate and deallocate at will. And that's a good starting point for building an exploit. In addition to this, we want to have buckets that appear at some point and buckets that appear at other points of the exploitation, like as you would have in steps in an exploitation. And to do this, I used buckets that were basically Russian dolls of chunked encoding, so that every time you call dchunk onto them, their size changes. As you can see in the example here, the first size that it will have is 108, then it will have a size of 100, and then it will be smaller than 100. And that gives you a way to resize buckets at will as the exploitation goes in, even though you're not actually interacting with the PHP server. So now we have basically everything that we need to build an exploit for controlling the free list. So we have a 1 byte overflow. We're going to use the overflow of value 48. We are going to focus on chunks of size OX100 because their LSB is always going to be 0. And also we want to overwrite the next pointer of the free list so that we can write at some arbitrary address. So the exploitation is really like standard, but I will still go through it. So you have three chunks initially, A, B, and C, or in this order, sorry. So A is the first one in the free list, then you have B, and you have C. And what we will do is allocate the 3 of them and then free them, which will give us step 3. And step 3 means that we have reversed the free list. We have C that points to B that points to A. And then we allocate C, and in C we're going to put an arbitrary pointer at offset 48. Okay? So here the arbitrary pointer is 1122 something, but it could be anything. Then we allocate B and then A, and we free everything, and we get into step 5. In step 5 we have exactly the same shape, as in step 1, but in C we have an arbitrary pointer at offset 48. So now, in step 6, we can overflow starting from A, and the 1 byte overflow will actually overwrite part of the pointer that is in B. And the pointer that is in B, it was pointing to C, so now it points to C plus 48, which is the address of the arbitrary pointer that we have written. So now with 3 more allocations, we allocate B, C plus 48, and then the arbitrary pointer, and that gives us a way to have an arbitrary write in memory. And from there, it's basically GG because, as I've said before, we know the address of the PHP heap, and there are some function pointers in there. And what we can do is do like the standard CTF thingy where we overwrite the free function, which is generally used to free memory, by system, so that when it calls free, it will actually call system, and it will allow us to run an arbitrary comment. So the performance of the exploit is that it will work against any target from PHP 7 to the current one. So that's 10 years of PHP covered for using a single binary exploit. So it's pretty cool. It works against any PHP application. You could be targeting like a huge CMS with a lot of traffic, or you could be targeting an indie website that everybody has forgotten about. It will still work. It's 100% reliable. You will never get a crash. Never. And also the payload is really small, because the first thing that we do is decompress it. So originally it's pretty small, so that means that it fits in GET requests. And also the last good point is that the exploit is completely self-contained. You don't need to send anything else. You just send your PHP filter string and you get a shell, which is pretty cool. And so this exploit effectively converts file read primitives into RCE in PHP. So a quick demo, I chose to target Cosmic Sting, which is a vulnerability that came out in June. It targets Magento, which is a huge e-commerce platform in PHP. It's an XXE, so it will let you read files. And it was originally used to read files and access secrets that let you create API keys. But using my exploit, you can actually get a remote code execution straight up. And this is what I'm going to try and show you. So it's a video, sorry, usually I do it live, but I couldn't find my Dockers, so I had to do it by video. So on the left you have a Magento website, on the top right you have the exploits, and on the bottom you will get a shell at some point. Yeah, there you go. There we go. Okay. How much time do I have left? Yeah, okay. So that was the first way of exploiting the Iconv calls, but there's another one, because in PHP you can also use the Iconv function to exploit Iconv calls. The problem here is that the exploitation is completely different. It's very much harder. So here, you don't have a file read, so you cannot use it to read proxf maps, you cannot read the binaries, like you have to do a normal binary exploit, where you try to get a leak, and then using that leak, you build a new exploitation technique that uses the leak to get code execution. The normal way of getting a leak in PHP is to overwrite the Zen string structure, which is the structure that will represent in C a PHP string. So if you create a PHP string, it will be stored as a Zen string. And the structure, it has a length field, which stores its length. Okay? It's immediately followed by the buffer. It's not a pointer to the buffer, it's the buffer itself. So that means that if you are able, using an overflow, to overwrite the length of a string, and if the string gets displayed afterwards, it will display way too much data, and you will be able to see what's in the heap, and that will give you your leak. The problem is that we have a really bad bug, as I've said numerous times before, and if we just trade up overflow into a Zen string, since the overflow is 3 bytes long, we will only overflow into the ref count, which is completely useless in our case. So to beat this, we need to actually do the same as before. We need to alter some free lists so that we have two chunks that overlap, and having two chunks that overlap, we can start overwriting a Zen string before it's displayed. So yeah, again, the steps: corrupt some free list, have two chunks overlap, allocate on top of some string before it's displayed, overwrite its length field so that it gets way bigger, and when it's displayed, it will display the rest of the memory as well. But for doing this, we actually rely on the code. Like beforehand, we could allocate filters, we could allocate buckets, we could like do many things to control the memory. Here, we only have a call to Iconv. Like, we don't have anything else. So after we send the parameters, we cannot do anything else anymore, and we have to rely on the code. And we have to use what I call code gadgets. To give you a better idea of code gadgets, say that you have this piece of code. So here, the bug, you can trigger it, okay? You have a call to Iconv, you control the output charset, you control the input data. So that's all you need, basically, okay? But afterwards, the script ends, so you have corrupted the heap, but you've not been able to use the corrupted heap. So to use actually the bug, you need another line, such as this one. This one, it will allow you to create as many strings as you want because it's an exploit statement, and that will give you a way to use the corrupted heap after it's been, modified. So let's go through a real-world exploit for this. I chose to focus on Roundcube because that was the first target that I found that was using Iconv in a way that let us attack it. It's an open source webmail. It's, I think, the most famous one for PHP. It's very much used. And so what it lets you do, which we'll actually call Iconv in the end, is that it lets you send an _2, an _cc, and _bcc parameters, which are the fields that you put in when you send an email. Okay, _2 is the emails you want, the email addresses that you want to send to. _cc is the carbon copy, and bcc is blank carbon copy. And in addition to this, you can send an additional parameter, which is _charset. And when you send it, Roundcube will convert every of these parameters to the charset that you've set. I don't know why it's there, but I mean, you can do it. So it gives us 3 ways to trigger the bug, which is nice. In addition to this, right after it has parsed the parameters, so it will verify that the email addresses are correct. If one of the email addresses is not correct, it will actually display an error message that says, well, this email is not valid, please change it, and then the email. So if you think about it, it's basically what I was telling you about before. We can use _2 to set an invalid email so that invalid email gets set, so the error message is set. And the idea now is going to be to try and override the length field of the invalid email before it gets displayed. And to do so, we use cc to trigger the bug so that we modify the list and we alter the free list. And then we use bcc to allocate a few chunks so that the free list is allocated and that we overwrite invalid email and we change its size. And right after the error is displayed and we get the memory leak that we wanted. So it should work in theory, but sadly for us, it actually doesn't because the error message is JSON encoded, which means that every byte that is not valid UTF-8 gets discarded. So I did everything like for nothing. But the idea is still pretty good. We just needed to find another way to, like another position to exploit it. The idea is that the string that we want to overwrite, we want to find a string that is not modified too much before it's displayed, because if it's modified too much, maybe it's going to remove the bytes that we want. So we need to find a string that gets created right before it's displayed. But the problem is that when we do this, we actually have a string that doesn't have a lot of gadget chains in between the creation of the string and then it's displaying. So that makes it really, really hard to exploit. But I was able to do so at some point. It took me, I think, a week to get the leak. So it was pretty annoying. And at that point, it's really easy to exploit because you know where you are in the PHP heap. And you also know how you can alter some free list because you've already done it for getting your leak. So getting RCE is not really hard. You can go for a data-only attack afterwards, just modifying some data in the heap, or you can go for a binary attack where the same way I did beforehand. The data-only attack, I think it's more classy. It's easier to do as well because you don't really have to care about the PHP version. It will work against any PHP version. So it's easier to do, I think. But all of this, it's a visible part of the iceberg. It's really, really hard to pull off, honestly, because I haven't talked about the heap setup, because if you want to have a free list that you can actually alter, you have to do a very, very precise heap setup. And the only way you can do this is by sending get and post parameters. But then, in between the bug that gets triggered and your HTTP parameters, there's been like 100 scripts that have been compiled and run. So the heap is completely modified. So it's really, really hard to pull off. In addition to this, every time a function is called, when you get out of the function, every variable that has been allocated, it has been allocated on the same heap as yours. So it gets deleted and it completely messes up the heap. So it's very, very annoying. And I think my exploit, if I just like so much as changed the output language, it wouldn't work. Like it's really, really precise. So it was generally a huge pain to pull off. Don't do this. I only did this to show that it was possible, but I don't think you should. Quick demo. Up. Same layout. You get a shell at the end at the bottom. So that's Roundcube. It's a posted exploit. You need like user credentials. So you need to be able to access the webmail. And then you get your shell again at the bottom. So you have control of the website. Yeah, quick conclusion. I think we have time. So yeah, really bad bug, but PHP, I mean, it's PHP. So you can use it to attack anyways. It gave us a new attack vector, which basically converts 5 read primitives to RCE in PHP against any application, so it's pretty cool. And also, it gave us application-specific attacks, even though it's pretty hard to pull off. But I also think that there are other targets hidden somewhere. Like, the bug is not specific to PHP, it's in the glibc, so there might be like other applications, completely different applications that actually use Iconv in a way that make it vulnerable. I just wasn't able to find one. So hopefully it will be discovered as time goes by. I don't know. Quick timeline, and also a shout out to the Glibc security team, because they were really nice, they were really fast, they were really competent. It's really hard to find even one quality such as this one when you report a bug, so it's nice. And yeah, I think in 1 week they had a patch rolling, and after 2 weeks embargo, they released the CVE. So yeah, I only had like 45 minutes, so I couldn't talk about many things. So if you're interested in, if you're interested into the subject, you can go onto my blog and onto our GitHub as well. There are every exploits there, and there's my Twitter if you have a question. And I think we're done. Yeah.
Thanks a lot, Charles, for your nice talk today. Any question for Charles? We have a bit of time. There's one here in the middle.
Yeah, incredible work, really. Very humbled. Just what would you tell the PHP people with regard to their heap management? How could they kind of change the heap management so that exploits like this could not happen?
Okay, that's a really good question. Actually, they are actually working on this right now. It was here last year, I don't know. Julien Voisin is not here. No. Okay, so he's working on this. Well, there's many things to do. Actually, you can just like do the same as the glibc, where you actually check that the chunk is really inside the heap before you try to dereference it. You can have cookies. You can do many things. And they're actually working on this. And there's also a good mitigation that is pretty fun. The heap setup, generally, you do it by sending get and post parameters. I couldn't cover it because we don't have time. But what they want to do is separate 2 heaps, one for the HTTP parameters and one for the real script, so that you cannot influence the heap beforehand. And this is really annoying, and they want to do it. So I think the next PHP version is going to come out. And also regarding PHP filters, they want to limit it to like 5 filters maximum, which is really annoying as well.
Yeah, I'm sure you'll get through. Thank you.
Any other comment or question? No.
Thanks.
So you were perfectly clear. Thank you, Charles, again.